Hello and welcome to another Ginger Mathematician video where we're going to go through questions 5, 6 and 7. Notice I've taken a part of the formula sheet for this particular question. So a garden has a triangular sunshade suspended from 3 points, so in 3D, 202, 802 and 543 relative to an origin in the corner of the garden. And these distances will be in meters, which makes lots of sense. And we're going to find the vectors first of all, CA and CB. So remember, in order to work these vectors out, we need to work from right to left. So this is going to be the vector A minus C when we convert the coordinates into vector notation. And likewise here, this is going to be B minus C. So let's work these out first of all. So CA, this is going to equal to, well, let's start with A. So this is 202. And then we're going to minus C from it, which is this over here, 543. And if we do this, remember, when we're minusing vectors, we minus the x, y, and z components separately. So 2 minus 5 is equal to minus 3. 0 minus 4 is equal to minus 4. And 2 minus 3 is equal to minus 1. And we do see B in exactly the same way. So we start with B as a vector, so 802. And then we're going to minus from that C, which is 543. And then if we do the same kind of subtraction we did earlier, we're going to get 3 minus 4 and minus 1. Like so. So once we've got that, then we can actually do the next part of the question, which is we're going to find what's called the vector product. So as soon as we timesing two vectors, we've got a choice here of a scalar product or a vector product. Because we've got the cross here, we're going to work out the vector product. And you'll see the formula on the right-hand side for this. So you're given this in the IBHO-AI exam. But before we use it, we need to understand exactly what's going on. So I'm now going to label each of these vectors. So we're going to start with our vector V. So this is the first one here, CA. So this is going to be V1, V2, and V3. And then we're going to take CB, and then we're going to label that W1, W2, and W3, like so. And at this point, what we're going to do is then put these values into our formula. So we're going to open up part B, and we're going to work out the cross product here of CA and CB by carefully putting these into the formula. So we start with V2 times W3, so that's going to be minus 4 times minus 1. And then we are going to do minus, and then let's look, so V3W2, so minus 1 times minus 4. Okay, and we'll come back to working that out in a second. And then we're going to do the second part, so V3W1. So notice I'm writing all this out very, very carefully. So minus 1 times positive 3 minus, and now V1W3 the other way around, so minus 3 times minus 1. And now we do the last part, V1W2. So that's going to be minus 3 times minus 4 minus the other way around, V2W1. So minus 4 times positive 3. So notice I've written this very carefully, so I'm trying to avoid making any mistakes. Now I'm going to do the brackets now. So minus 4 times minus 1 is equal to 4. And then we're going to get minus, and we're going to get minus 1 times minus 4, so that's equal to positive 4. And then the next part, so minus 1 times 3 is minus 3. Minus 3 times minus 1 is equal to positive 3. And then the last part, so that's equal to positive 12 minus, and minus 4 times 3 is minus 12. So very, very careful with the signs, making sure I'm doing each step quite clearly. I know it's a 2-mark question, but you don't want to make a mistake. 4 minus 4 is equal to 0. Minus 3 is equal to minus 6. And then finally, 12 minus minus 12 is equal to positive 24. And we have our answer there. Now using this, we want to now find the area of the triangle ABC. So notice we've got the formula over here for the area of a parallelogram, which is we take the cross product of two adjacent sides of the parallelogram. Well, you can draw a diagram to show you this, but you'll notice CA and CB fit that description. However, we do not want to work out a parallelogram, we want to work out a triangle. So what we need to do to work out the area of the triangle is use the same formula, so the magnitude of V cross W, but then we want to divide that by 2. So what we need to do here is take the answer from before. We want to find the magnitude of that vector. So remember, to work out the magnitude of the vector, we do essentially Pythagoras. So we've got minus 6 all squared plus 24 squared. And then we're going to take that entire answer and then we're going to divide by 2. So I'm going to go over to my calculator now and work that out. So let's pop this in. So I've got my normal calculating view open here. So we want to do the square root of, and I'll make sure I put this in brackets, minus 6, close brackets, all squared, plus 24 squared. Get an answer. And then we want to take that answer and divide that by 2. And we get the answer of 3 root 17. Now, generally on this kind of AI paper, I'm going to write this without surd form. So I'm going to press Control Enter here, and this will allow me to get this as a decimal. So we get 3 root 17, which we can then write as 6 point. I've divided by 2, so you just want 3 root 17. Don't know why it's divided twice. That's kind of strange. So if we do 3 times root 17, or take that answer and times it by 2, that's going to give us the answer. Control Enter. There we are, of 12.3693. So I'm going to write that down. So we get 12.3693. And remember, on this paper, you always need to put your answers to 3 significant figures. So we're going to write this as 12.4. And remember our units here, meters squared. As I said right at the start of the question, we are working in meters. So make sure you're very clear to the examiner that you've put the answer, the correct answer of 12.4. Okay, and you can see the mark scheme in front of you, so where you're picking up the method marks. Okay, so I've written out my working very clearly for part B. Just in case you make a mistake, so you're going to guarantee that method mark there for you as well. Okay, question 6 is a kind of sneaky question. So a triangular field ABC is such that AB is 56 meters, BC is 82, so given on the diagram, each measured correct to the nearest meter. That's really important. And the angle at B is equal to 105 degrees, given here, measured correct to the nearest 5 degrees. And what we're looking for here is the maximum possible area of the field. Okay, so we need to think how it's been rounded and then find the upper bound of the various different bits that we need for the formula. Now, the formula for the area of a triangle, you should know this from IGCSE or before, is equal to half AB sine C, also on your formula sheet. So because we want the maximum, we need the upper bound of these two values here to start with. So remember, this is rounded to the nearest meter. So our upper bound here is going to be 56.5, because everything below that would be rounded down to 56. Likewise here, the upper bound is going to be 82.5. And this is where the question gets a bit tricky, because we have this angle here and we want to find the upper bound. However, we want to find the upper bound for the sine of that particular angle. Okay, now on the surface you might think, well, that's going to be, because it's nearest 5 degrees, it's going to be sine 107.5. Because everything from that will be rounded down to 105, everything from there will be rounded up to 110. But that's not actually the case. Let's be careful here of how the way the sine function works. Okay, so if we look for the so-called lower bound of 105 on its own, that would be 102.5. But if you actually work out these answers, you're going to get a bit of a surprise. So if I type in, and make sure this is in degrees, so if I type in sine of 107.5, you'll see that you get an answer of 0.9537. If you type in, however, the sine of 102.5, that's actually equal to a higher number. Notice it's actually equal to 0.97. And that's because of how the sine function works. So it gets to its maximum point at 90 degrees and then gets smaller from there, which is why actually the sine of 102.5 is actually bigger than the sine of 107.5. Okay, but hopefully these values show you exactly why you need to take 102.5, because that will give you then the maximum value of the area of the triangle. So this is the important part that we need. This is actually bigger. So let me write this in. So this number is actually bigger than this number here. So just going to write myself a reminder here that sine 102.5 degrees is actually bigger than sine 107.5, because we want to work out the maximum. So now we've got everything in place. Now we just put this into our formula. So we've got half times 56.5 times 82.5. And this is the crucial part here. We actually want sine of this because it gives us a bigger number. And at this stage, we now just put this into our calculator. So we're going to type in 0.5 times 82.5 times 56.5. And this is the important part here. So we want sine. You can also write SIN as well. That also works. Make sure your calculator is in degrees. That is very important. And then we're going to get our final answer of 2,275.38. Mine's at float 6. You probably should have a bigger float, but it will be fine for this question. So we get 2275.38. ... And remember here, we always round to 3 significant figures. That's really important. So this is going to be 2,280. Remember, the units are in meters, so we need meters squared to 3SF. You do need this precision at IB exams, making sure you're rounding to 3 significant figures, and also that you are putting the correct units, in this case, square meters. Okay, and you can see the mark scheme here and see where you pick up those 5 particular marks. Notice the accuracy mark right at the end. And on to question 7. So Ellis here designs a gift box, and the top of the gift box is in the shape of a right angled triangle GIK, so the entire thing. A rectangular section HIJL is inscribed within the triangle, and then you're given various lengths for the similar triangles here. That's kind of a clue later on. And the area of the top of the gift box is equal to A. Okay. And the first thing we need to do is work out what A is in terms of P and Q. So if we take our diagram, we can work out the area of the rectangle easily. That's 8 times 6, which is equal to 48. And now if we work out the area of this triangle, remember this is also a right angle, so you don't need to do anything too complicated here. We just use the formula of half base times height. So 8 times P divided by 2, that's equal to 4P. And then 6 times Q, remember this is also a right angle, divided by 2, and so that's equal to 3Q. So if I go to my next slide here, for part A, the area in terms of P and Q, well, we just add all these together, so we get 48 plus 4P plus 3Q, like so. And now we need to show that the A is equal to this expression here. This is a very typical optimization question, as you'll see in parts B and C. And notice this is almost identical to what we have here, apart from instead of a 4P, like we had in our original formula, we've got a 192 divided by Q instead. So what we need to do is find a relationship between P and Q, an equation with both P and Q. And then from there, we can actually then substitute into our original formula. And then we get thinking, okay, how can we actually do this? And how can we actually see this relationship here? And notice that these two angles here, because of similar triangles, are actually the same angle. Okay, or likewise, you could take this angle instead. They are also the same angle. Now you can show this using angles in parallel lines. Okay, but you can probably see that they're both right angle triangles and in the same proportion. If that's true, then we can actually use SOHCAHTOA on this. Notice this is our opposite side, this is our adjacent to this angle, and likewise here, this is opposite and this is adjacent. So we can use tan twice here to actually generate an equation. So if I take the first triangle, well, tan theta, I'm using tan because I have opposite and adjacent, is equal to opposite, which is 6, divided by adjacent q. I can also do exactly the same thing over here. So tan theta is equal to opposite, which is p, divided by 8. Okay, so you can actually write both of these tans of these angles in terms of p and q. So let's write that on the other slide. So we have the part, this is part 2, isn't it? So this is part 1. So we'll continue on here. So we have tan theta is equal to 6 over q. And we also have tan theta is equal to p over 8. That means if they're both equal to tan of the same angle, the two things here must also be equal. So 6 over q must also be equal to p over 8. And from here, we can just do some cross multiplying. So because we have fraction equal fraction, we can cross multiply. So it means p times q is equal to 8 times 6, which is 48. And because we want to change the p to a q, we need to write p in terms of q. So I'm going to divide by q on both sides of my equation. If I do that, this cancels here. We have p equal 48 divided by q. At this stage, I'm just going to get my highlighter out here. I'm going to replace the p in my initial formula with 48 over q because they're both equal to p. So I'm just going to write exactly the same equation up here. So a is equal to 48 plus, now wherever I see a p, I can replace it with a 48 over q, keeping everything else the same. And then all we need to do here is just times 48 by 4. So we get 48 plus, now you can obviously do this on a calculator, but 48 times 4 is equal to 192 over q plus 3q, which is exactly what we needed here. Notice it's just in a slightly different order. Okay, so you've got the 48 at the end instead. So we've done this part and done this part. Now at this point we need to differentiate, so dA by dq. Now before we do differentiate for part B, I'm just going to write this slightly differently. So I'm going to write this as A equals, well, we can put this into index notation. So we've got 3q, that still stays the same. Remember, anything over q is the same as q to the power of minus 1. And then I'm going to put the 48 over here. So it's all set up ready for the differentiation process. So then I work out what dA by dq is equal to. So remember the differentiation process. If you just have a linear function, so to 3q, this just becomes 3 because you reduce the index by 1. Q to the power of 0 is 1. If I differentiate this, well, I'm going to get minus 192. But I need to reduce the index by 1, so this becomes minus 2. And remember, if you differentiate a number, that then just disappears. So this is my answer here. So 3 minus 192 q to the power of minus 2. And if we go on to part C, Ellis wishes to find the value of Q that will minimize the area of the top of the gift box. And now we need to write an equation could solve to find this value of Q. So as soon as you see this word minimize or maximize, then we need to take the differential of A respect to Q is equal to 0. That's what you need to trigger in your mind. So in this case, if you go to part C, we're going to set that equation, so 3 minus 192 q to the power of minus 2, we're going to set that to 0. So for part C, 3 minus 192 q to the power of minus 2 is equal to 0. Once we have our equation, now we need to actually find the value of Q. Now there are many different ways you can do it at this point. The way I'd approach this is doing it algebraically, but you can also use your graphical calculator at this point. So what I'm going to do is going to add that on both sides. So I'm going to add 192 q to the power of minus 2 on both sides. Again, many ways of approaching this. So we get then 3 is equal to, well, this cancels, 192 q to the power of minus 2. Now remember, q to the power of minus 2 can be rewritten as 192 over q squared. So kind of in reverse of what we did for the differentiation. And then I'm going to multiply by q squared on both sides. At this point, we're going to standard equation territory. So 3 times q squared is 3q squared. And this cancels, which is great. So we just get 192 here. Now we're going to divide by 3 on both sides. So this cancels here. So that gives us then q squared. If we divide that, I can do it in my head, I'm sure. I think that's 64. And now if we square root our answer, so we're going to square root on both sides. Again, this cancels. So we get q is the square root of 64. So we have to be slightly careful because, strictly speaking, the answer is plus or minus 8. But remember, if we go right back to the question here, we're talking in terms of lengths. Notice that q can't be minus 8 centimeters or minus 8 meters, centimeters in this case. So we have to take the positive answer. So q is going to be equal to 8 centimeters. Okay, that is the only answer that can exist in the real space, i.e. working with a gift box that we have. Okay, hope you enjoyed that video, and be ready to check out also questions 1 to 4 as well if you haven't seen those already.